Hold an ice cube. Feel that cold biting into your skin, that sharp sting crawling up through your fingers. You know exactly what's happening. The ice is cold, your hand is warm, heat flows out. Simple, obvious, done, except Feynman looked at that same ice cube and saw something completely different. He didn't see cold. He saw a battlefield. Right now, inside that ice, billions of atoms are locked in a war that's been raging since the universe began. On one side, Jiggle, that restless thermal energy shaking every atom, vibrating, bouncing, desperate to break free. On the other side, Stick, the electrical attraction pulling atoms together, forcing them into rigid formation, and freezing is the moment Stick wins. Atoms surrender their freedom. They lock into place. They form ice. But here's what nobody tells you. That surrender isn't quiet. It's violent. Every atom that locks into crystal releases energy. Heat. The very thing you thought freezing would remove, freezing actually creates. Freezing doesn't cool things down. It heats them up. Your freezer right now is getting hotter because the ice inside is releasing heat as it forms. That warm air blowing from the back of your fridge, that's the heat of war. The heat of atoms losing their freedom. And in the next 35 minutes, we're going to follow Feynman into this atomic battlefield. We'll watch Jiggle and Stick collide. We'll ask what happens in a universe where Jiggle always wins, where nothing ever freezes, where life itself is impossible. We'll uncover a paradox that baffled scientists for decades: hot water freezing faster than cold. And we'll come back to that ice cube in your hand and finally understand what's really happening when cold bites your skin. This is the story of water freezing, and nothing about it is what you think. So before we follow Feynman into the atomic world, we need to kill an idea that's been dead for 200 years, but still haunts every textbook. Caloric. For centuries, scientists believed heat was a substance, an invisible fluid called caloric that flowed from hot objects to cold ones, like pouring water from one cup to another. Heat had weight. Heat had volume. Heat was a thing, and honestly, it made sense. Touch a hot stove, something flows into your hand. Drop ice into warm water, something flows out. Caloric explained everything until it didn't. 1798, Munich. A man named Count Rumford is standing inside a cannon factory, watching workers bore out brass cannons, and he notices something bizarre. The metal shavings aren't just hot, they're scalding, boiling water hot, and they never stop. If heat were a fluid, caloric, the metal should run out of it eventually, like squeezing a sponge dry. But Rumford kept boring, and the heat kept coming. Endlessly. The brass never ran out of heat because heat was never inside the brass to begin with. He published his findings. Heat is not a substance. Heat is motion. The atoms themselves were shaking. Friction wasn't releasing caloric. It was making atoms jiggle faster. But it took another 50 years for anyone to prove it. James Joule, a brewer from Manchester, built a device with a paddle wheel inside an insulated tank of water. See, a falling weight turned the paddle. The paddle churned the water, and the water's temperature rose by exactly 1 degree Fahrenheit, 0.56 degrees Celsius, for every 772 foot-pounds of work. No fire, no flame, no caloric, just mechanical motion converting into heat. Joule proved it with data precise to 3 decimal places. Heat is motion. And that single insight, that heat is just atoms jiggling, is the key that unlocks everything Feynman will show us next. Richard Feynman once said, and I'm going to quote this exactly because he chose every word with surgical precision. If, in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation, what statement would contain the most information in the fewest words? His answer: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. That's it. One sentence. And buried inside it are the two forces we met in the hook: jiggle and stick. Perpetual motion, that's jiggle. Attracting each other, that's stick. Feynman packed an entire war into 42 words. Now let's actually see what Feynman described. A water molecule, H2O, looks like Mickey Mouse's head. One big oxygen atom with two small hydrogen atoms stuck to the ears at a 104.5 degrees angle. You picture a room full of these Mickey Mouse heads. Billions of them. And they're all drunk. Seriously. Imagine the world's most chaotic dance floor. Every molecule is stumbling, spinning, crashing into its neighbors. Some slam together and bounce apart. Some grab onto each other for a moment before getting knocked loose again. That's liquid water. That's what's happening right now in every glass, every puddle, every ocean on Earth. The speed of this chaos? I'm at room temperature, about 20 degrees Celsius, 68 degrees Fahrenheit. The average water molecule is traveling at roughly 590 meters per second. That's 1,320 miles per hour, faster than a bullet. But here's the critical insight. Temperature isn't what you think it is. Temperature is not how much heat something has. Temperature is how hard molecules hit each other. It's the average kinetic energy of collision. The harder they slam, the higher the temperature. The gentler they drift, the lower. And now, I want you to do something. Hold an ice cube again, or just remember the feeling from the hook. That cold biting into your skin, that's not cold entering your body. Cold isn't a thing. Cold doesn't flow. What you're feeling is heat, your heat being stolen. Billions of water molecules in that ice are jiggling slowly, barely moving. But the molecules in your skin are screaming past at hundreds of meters per second. When they collide at the boundary, your fast molecules transfer their kinetic energy to the ice's slow molecules. Your skin loses jiggle. The ice gains jiggle. That sting you feel? That's your atoms slowing down. That's jiggle leaving your body. And here's what makes this so beautiful. This is exactly the same war we described in the hook, just zoomed in. Jiggle versus stick. Your body's jiggle flowing into the ice, making its molecules vibrate faster, weakening stick's grip on the crystal structure. You're not just holding ice, you're fighting a war, and losing. Now that we know what heat really is, what atoms really do, and what temperature really means, we're ready. Ready to watch Jiggle and Stick collide head-on. Ready to see what happens when water actually freezes. So let's zoom in, closer, past the glass, past the surface, down to the molecules themselves. A water molecule isn't neutral. It's a tiny magnet. Remember Mickey Mouse's head? That big oxygen atom with two hydrogen ears? Here's what makes it special. Oxygen hogs electrons. It pulls the shared electrons closer to itself, leaving the hydrogen ends slightly positive and the oxygen end slightly negative. Chemists call this polarity. Feynman would call it the reason everything interesting happens. Because when one molecule's positive hydrogen drifts near another molecule's negative oxygen, they grab each other, not with hands, with electrical force. Now, a hydrogen bond, roughly 23 kilojoules per mole, about 5.5 kilocalories. Tiny. But multiply that by trillions of molecules, and you get an army. And now, the war. Inside that glass of water on your desk, there is a war. A constant billion-year-old war. On one side, jiggle, thermal energy. Every molecule vibrating, spinning, slamming into its neighbors at 590 meters per second. 1,320 miles per hour. Jiggle wants chaos. Jiggle wants freedom. Jiggle tears every bond apart the instant it forms. On the other side, stick, electrical attraction. Those hydrogen bonds reaching out, grabbing, pulling molecules into formation. Stick wants order. Stick wants crystal. Stick tries to lock everything into place. And in liquid water, neither side wins. Grab, break, grab, break, trillions of times per second. A hydrogen bond forms, lasts about 1 picosecond. That's 1/1,000,000th of a second, or 0.0000000000001 seconds. Then jiggle rips it apart. Another forms. Another breaks. An endless stalemate at the molecular scale. That's what liquid water actually is. Not calm, not peaceful. A furious, raging tie. Now, you open your freezer, you slide in a glass of water, you shut the door, what happens? Cold air, around -18 degrees Celsius, 0 degrees Fahrenheit, surrounds the glass. Air molecules at that temperature are sluggish, drifting slowly. When they collide with the glass, they steal kinetic energy from the water molecules inside. Like a billiard ball hitting a slower ball, energy transfers. Your water molecules start losing speed from 590 meters per second to 500 to 400, and the war begins to turn. Every degree the temperature drops, jiggle gets weaker. The molecules vibrate less violently. The hydrogen bonds last a little longer, 2 picoseconds instead of 1. Then 5, then 10. Stick is gaining ground. The jiggle is fading, the stick is tightening. And what does stick build when it finally wins? When something extraordinary. Here's what most people imagine when water freezes. Molecules just stop. They slow down, pile up randomly, and become solid. Like a crowd freezing in place during a game of musical chairs. Wrong. When stick wins, it doesn't just stop the molecules. It organizes them. It builds something. Something with architecture. Something with geometry. Something with a plan. Freezing isn't collapse. Freezing is construction. Remember the 104.5 degrees angle between those hydrogen ears on Mickey Mouse's head? That angle isn't random. It's a blueprint. When molecules slow down enough for stick to take control, that 104.5 degrees bond angle forces them into a very specific arrangement. Each oxygen atom connects to 4 neighbors through hydrogen bonds, 2 through its own hydrogens, 2 through its oxygen. And that 4-way connection, repeated billions of times, creates hexagons. Perfect 6-sided hexagons. Honeycomb rings of water molecules stacking outward in every direction. Not a random pile. A cathedral. A crystalline cathedral of ice with vaulted arches and geometric precision that would make any architect weep. And here's the twist that changes everything. Those hexagonal rings, they have space inside them. Empty space. Gaps. The honeycomb structure is less dense than liquid water. About 917 kilograms per cubic meter versus 1,000 kilograms per cubic meter. That's roughly 57 pounds per cubic foot versus 62 pounds per cubic foot. Think about what that means. Ice is less dense than water. Ice floats. That sounds obvious. You've seen ice cubes floating your whole life. But stop and realize how absolutely bizarre this is. Almost every other substance in the universe does the opposite. Solid iron sinks in liquid iron. Solid gold sinks in liquid gold. Solid rock sinks in liquid rock. When things freeze, they get denser. They sink. Water breaks the rule. And that rule breaking saved every living thing on this planet. Imagine if ice sank. Every winter, the top of a lake freezes, and the ice sinks to the bottom. More water freezes on top. That sinks too. Layer after layer, the entire lake freezes solid from the bottom up. Fish, dead. Microorganisms, dead. The entire aquatic ecosystem, gone. But because ice floats, it forms a lid, an insulating layer on top, only about 5 to 15 centimeters thick, 2 to 6 inches, that protects the liquid water below. Fish swim. Microorganisms thrive. Life survives the winter. That 104.5 degrees angle, that one quirk of molecular geometry, is the reason life exists on Earth. Beautiful, right? But here's the paradox. You just watched Stick win the war. Molecules surrendered their freedom, locked into honeycomb crystal, became ice. And your intuition says, that's cooling. Freezing means getting colder, energy leaving, things calming down, wrong. Freezing is one of the most energetically violent things that happens in your kitchen. And to understand why, we need to think about what happens to all that jiggle energy when molecules stop moving. Imagine a car doing 100 kilometers per hour, about 62 miles per hour, on a highway. Now slam the brakes. The car stops. But the energy doesn't vanish. It can't. Physics won't allow it. That kinetic energy converts into heat. Your brake discs glow red. Touch them, and you'll burn your hand. Now picture a water molecule doing the same thing. It's been flying around at 590 meters per second, crashing into neighbors, full of jiggle, and then Stick grabs it, locks it into crystal, forces it to stop. But the energy, the jiggle, has to go somewhere. And here's the number that breaks people's brains. Every single gram of water that freezes releases 334 joules of energy, about 80 calories. That's called the latent heat of fusion. Latent meaning hidden, hidden heat. Think about that. 1 gram. That's roughly 20 drops of water, and it dumps enough energy to heat another gram of water from 0 degrees Celsius all the way to 80 degrees Celsius, from 32 degrees Fahrenheit to 176 degrees Fahrenheit. From ice cold to nearly boiling, from a single gram freezing. Now multiply that by every gram of water in your ice tray. A standard tray holds about 300 grams, 10.5 ounces. That's over 100,000 joules, 100 kilojoules, of heat dumped into your freezer every time you make a batch of ice cubes. And this is why your freezer's compressor kicks into overdrive every time you add water. Listen for it next time. Slide in a tray of water and wait. Within minutes, you'll hear the compressor rev up, working harder, burning more electricity, pumping that dumped heat out through the coils on the back of your fridge. Touch those coils. They're warm. That warmth? That's the heat of atoms surrendering, the heat of jiggle being expelled as Stick takes over. The act of freezing is an exothermic process. Your ice is literally heating up the freezer. And here's what stalls the whole process. At exactly 0 degrees Celsius, 32 degrees Fahrenheit, the temperature flatlines, stops dropping for minutes, sometimes longer. The water isn't getting colder because it's too busy dumping its latent heat. Every molecule that locks into crystal releases energy that warms the surrounding water back up. It's a tug-of-war within a tug-of-war. Stick winning the structural battle while Jiggle fights back thermally. The temperature doesn't drop again until every last molecule has surrendered its heat. So freezing isn't quiet. Freezing isn't passive. Freezing is a controlled explosion of energy disguised as stillness. But wait. We've got a bigger problem. Forget the heat for a moment. Look at the structure. Look at what Stick just built. Perfect hexagons. Repeating crystal lattice. Geometric precision extending in every direction. That's order. Pure, stunning, molecular order. And if you've ever taken a physics class, or even just heard the word entropy, alarm bells should be ringing right now. Because the second law of thermodynamics says the universe moves in one direction, toward disorder, toward chaos, toward entropy. So how does water, chaotic, messy, liquid water, spontaneously organize itself into a perfect crystal? Isn't that entropy running backward? This isn't a small question. This bothered some of the greatest minds in physics, because on the surface, it looks like freezing violates the most fundamental law of the universe. Here's where Feynman's thinking cuts through the confusion like a blade. Yes, the ice cube is more ordered than the liquid. Entropy of the water went down. That's a fact. And no, that doesn't violate the second law, because you forgot to count the tax. Remember those 334 joules per gram? That latent heat that every freezing molecule dumps into the surroundings? That energy, that heat, flows into the air inside the freezer, into the coils, into your kitchen. And when that heat hits the air molecules, they speed up, they scatter, they become more disordered. The ice gained order, but the air gained chaos. A lot of chaos. And when you do the math, the entropy increase of the surrounding air is always greater than the entropy decrease of the ice. Always. Without exception. Every single time water freezes anywhere in the universe, the total entropy goes up. A tiny pocket of order, purchased with a huge amount of disorder everywhere else. The house always wins. And you can actually watch this war play out, right at the boundary where liquid meets solid. Physicists call it the freezing front. Imagine the edge of the ice crystal growing outward into liquid water. It's not a clean, smooth wall. It's a jagged, fractal mess. Molecules at the boundary are caught between two worlds, Stick pulling them into crystal, Jiggle knocking them loose again. Some molecules land on the crystal and stay. Some land and get ripped off within picoseconds. Some hover at the edge, half-locked, vibrating, undecided. It's a statistical game, billions of coin flips per second. When the front advances when Stick wins more coin flips than Jiggle. It retreats when Jiggle fights back. On average, at minus 18 degrees Celsius, 0 degrees Fahrenheit, Stick wins just slightly more often than it loses, and the crystal creeps forward, one molecular layer at a time. It's like rearranging deck chairs on the Titanic, except in this case, the rearranging actually works. One molecule at a time, Stick builds its cathedral while the universe around it burns hotter. And somewhere in that jagged, chaotic, beautiful freezing front, there's a mystery that scientists argued about for over 50 years. A paradox so strange that it was named after a Tanzanian schoolboy. But that's the next chapter. Now, here's something that should keep you up at night. Show someone a video of planets orbiting the sun, played backward. Can they tell? No. The physics looks identical. A pendulum swinging backward? Perfectly normal. Billiard balls colliding in reverse? Indistinguishable from forward. At the deepest level, the laws of physics don't care about the direction of time. Every equation works exactly the same whether time runs forward or backward. But show someone a video of an ice cube melting, played backward. Instantly, they know, everyone knows. A puddle of water doesn't spontaneously suck heat from the air, leap upward, and reassemble itself into a perfect crystal. You've never seen it. Nobody has. Nobody ever will. Why? The laws of motion allow it. Every single molecular collision is reversible. So why can't an ice cube unmelt? Because of probability. Picture this. You're standing on a diving board over a swimming pool. You jump. Water explodes outward, billions of molecules spraying in every direction, chaotic, random, violent. Now imagine that same explosion happening in reverse. Every molecule, billions of them, spontaneously hitting your body at exactly the right angle, at exactly the right speed, at exactly the right moment, to launch you back onto the diving board. Could it happen? Technically, yes. Not a single law of physics forbids it. Every individual collision is reversible, but the odds against it are so absurd, so incomprehensibly vast, that you could wait longer than the age of the universe, and it would never happen. Not once. The number of ways molecules can be disorganized is practically infinite. The number of ways they can be organized to throw you upward, vanishingly tiny. And that's exactly what freezing is. We're not breaking the laws of physics. We're rigging the odds. We rob the system of energy via the freezer so that the organized state becomes the only option left. We force the deck of cards to be sorted by removing all the room on the table for them to be messy. Freezing is coerced probability. Jiggle doesn't lose because Stick is stronger. Jiggle loses because we stole its ammunition. And here's one more paradox that will keep you awake tonight. 1963, Tanzania. A 13-year-old schoolboy named Erasto Mpemba is making ice cream with his classmates. The instructions say, heat the milk, add sugar, let it cool, then put it in the freezer. But Mpemba is impatient. He skips the cooling step, slides his hot mix straight into the freezer, and it freezes first, before his classmates' cooled mixtures. Hot liquid, freezing faster than cold. His teacher laughed at him. His classmates laughed at him. That's Mpemba's physics, they joked. But Mpemba kept asking, kept pushing. And when a visiting physics professor named Dennis Osborne came to his school, Mpemba asked the question publicly. Osborne didn't laugh. He went back to his lab and tested it. Mpemba was right. Under certain conditions, hot water can freeze faster than cold water. We call it the Mpemba effect. It's been replicated hundreds of times, peer-reviewed, published. And here's the strangest part. After more than 60 years of research, we still don't fully understand why. Some say convection currents in hot water distribute heat more efficiently. Some say dissolved gases escape from hot water, changing its freezing dynamics. Some say supercooling effects differ between hot and cold starting temperatures. Some say evaporation reduces the mass of hot water, giving it less to freeze. Nobody has a definitive answer. Nature, once again, is more complicated than our models. A 13-year-old boy noticed something that the entire physics establishment missed, because he wasn't afraid to look stupid. That's science. That's Feynman's spirit. Now, I said atoms are locked in place inside ice. I want you to be very careful with those words, because they are not still. Nothing in the universe is still. If you could shrink yourself down, past the crystal, past the hexagonal rings, all the way into the lattice itself, it would be deafening. The atoms are trapped. Yes, caged in their hexagonal positions by Stick's electrical bonds, but they are shaking, vibrating furiously against those bonds, rattling their cages like prisoners banging on bars. Ice isn't silence. Ice is a scream you can't hear. At your freezer's temperature, around -18 degrees Celsius, 0 degrees Fahrenheit, the atoms vibrate at roughly 10 trillion times per second. That's 10 trillion oscillations every second. Locked in place, but never still. So here's the obvious question. What if we cool it further? Way further. All the way down to absolute zero, -273.15 degrees Celsius, -459.67 degrees Fahrenheit. The temperature where all thermal energy is supposed to vanish, where Jiggle is supposed to die completely. Does the vibration stop? No, it cannot. And this is where classical physics dies, and quantum mechanics is born. Werner Heisenberg proved something disturbing in 1927. You cannot simultaneously know exactly where a particle is and exactly how fast it's moving. There's a fundamental limit to knowledge itself, not because our instruments aren't good enough, but because the universe doesn't have precise answers to both questions at the same time. If an atom stopped completely, zero velocity, zero momentum, you'd know both its exact position and its exact motion. Heisenberg says no. The universe forbids it, so even at absolute zero, atoms do a quantum jiggle. A zero-point vibration, tucked in an unkillable buzz of energy that exists because the universe refuses to allow perfect stillness. They're not hard little marbles sitting in fixed positions. They're fuzzy clouds of probability, smearing themselves across space just enough to satisfy the uncertainty principle. And there's a substance that proves this in the most dramatic way possible. Helium. Cool helium to absolute zero at normal pressure. Every other element in the periodic table freezes solid long before this point. Cold helium? It stays liquid, refuses to freeze, even at the coldest temperature the universe allows. Why? Helium atoms are tiny, incredibly light, and their quantum jiggle is so violent, so energetic, that it shakes apart any crystal structure that tries to form. Stick tries to grab. Quantum jiggle says no. The zero-point energy overwhelms the electrical bonds. Jiggle, in its quantum form, is literally unkillable. Even when you remove every last bit of thermal energy, the quantum jiggle remains, buzzing, waiting. Water is heavier. The oxygen atom is an anchor, so Stick wins. But the jiggle is always there. Even in the deepest, coldest ice, Jiggle never truly surrenders. It just changes form. Now let's step back. Let's look at this whole process. This war of Jiggle and Stick, this geometry, this probability, and ask, what does it mean for US? Remember that 104.5 degrees angle, the one that forces water molecules into hexagons, the one that makes ice expand instead of contract. That angle saved your life. If water behaved like virtually every other substance, if ice were denser than liquid, it would sink. Every winter, the surface of a lake would freeze and drop to the bottom. More water would freeze on top. Drop again. Layer by layer, the entire lake would become a solid block of ice from the bottom up. Oceans, too. Fish, gone. Microorganisms, gone. The entire chain of life that started in water erased. But water breaks the rule. Ice floats. And that floating lid, that thin sheet of hexagonal crystal, insulates the liquid below. Life survives the winter. Life survives the ice ages. Life survives because one molecule has ears at a funny angle. We are here because of 104.5 degrees. And here's the part that will change how you see yourself. You, right now, sitting there watching this, are doing exactly what that ice cube does. You are an ordered structure, a staggeringly complex pattern of atoms that persists in a universe determined to grind everything into dust. How do you survive? The same way the ice forms. You pay the tax. You take in high-quality energy, food, about 8,700 kilojoules, 2,000 calories, per day. You use it to build and maintain your internal structure, repairing cells, firing neurons, pumping blood, and you dump low-quality energy back into the universe. Body heat, roughly 80 watts of thermal radiation streaming off your skin right now, about as much as a light bulb. You are a heat engine, a biological freezer. You freeze chaos into order inside your body and pay for it by heating up the room. When you look at that ice cube, you are looking at a mirror of your own existence, a temporary triumph of geometry over chaos. Stick winning. For now. Now imagine the opposite. Imagine a universe where Jiggle always won, where thermal energy was always too strong for electrical attraction to overcome, where nothing, ever, could freeze. No ice, no crystals, no minerals, no rocks beneath your feet. Without solids, no planets could form. Every star would be a diffuse cloud of gas, never dense enough for nuclear fusion to ignite. No sunlight, no warmth. The entire universe would be a lukewarm soup of wandering atoms, drifting endlessly, never touching long enough to build anything, never forming a bond, never creating a structure, never producing a single snowflake, a single grain of sand, a single living cell. That ice cube in your freezer, it's proof that geometry can win. Proof that in this universe, our universe, stick is strong enough to fight back. And everything you've ever stood on, everything solid you've ever touched, every bone in your body, every tooth in your mouth, exists because of that fight. Think about what we've described. Choose atoms tangled in chaotic spaghetti, then straightening into parallel strands as temperature drops. The freezing point is just the corner where the geometry changes. The atom doesn't know it's making ice. It doesn't know it's cooling your drink. It's just following the local traffic laws of physics. And out of these simple local rules emerges the snowflake. Out of the chaos comes the beauty. So the next time you hear the clink of ice in a glass, don't just ignore it. That sound is the echo of a billion-year-old war. That sound is the release of latent heat, 334 joules per gram, trapped in the liquid, screaming out as atoms surrender their freedom. That sound is the universe settling down, one hexagonal ring at a time. You are holding a piece of quantum geometry in your hand. It is vibrating with zero-point energy. That unkillable quantum jiggle that Heisenberg proved can never stop. See, it is fighting to stay organized against the relentless thermal bombardment of the room. And it is losing, slowly, beautifully, melting back into chaos as Jiggle reclaims its territory, one molecule at a time. It is a little monument to the weirdness of nature, a temporary cathedral, a war memorial. Physics isn't about memorizing formulas. It isn't about knowing that water freezes at 0 degrees Celsius, 32 degrees Fahrenheit. That's just bookkeeping. Feynman would have hated that. Physics is about the imagination. It's about being able to close your eyes and see the jiggling, to see the electric springs snapping molecules into hexagons, to see heat flowing like a river of motion from your warm hand into cold crystal, to see a universe that looks simple on the surface but is raging with invisible war underneath. Why does water freeze? Because the universe is cooling down. And in its slow, inevitable exhale toward maximum entropy, it allows matter to snuggle together and dream of geometry. That's the miracle hiding in your freezer. That's the war inside every ice cube. That's what Feynman saw when everyone else saw just ice. And that is why I love physics. It turns the mundane into the miraculous. If this changed how you see something as simple as ice, tell me in the comments. What part blew your mind? The exothermic paradox? The Mpemba mystery? Or the fact that quantum jiggle never stops? Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just imagination. And next time you open your freezer, try to see the jiggling. I'll see you in the next one.